Hello everyone, welcome back. In this lecture, we're going to be discussing about an interesting type of algorithm for string matching. Previous lecture, we discussed about the string matching problem and a naive string matching algorithm. So as you can see, in a string matching problem, we have been given a text and we want to match up the pattern string and find out how many times or where this pattern occurs in the text string. All right, and we discussed about what are different types of algorithms and the basic general overview about a string matching problem in the previous lecture. So the, this lecture we focus in this lecture we're going to be focusing about another class of algorithms which we call as finite automata or finite automation based algorithms. So what essentially is a finite automation, okay, or finite automata? Well, it's a five tuple, okay. In short, as you can see, um, that that we have here the five tuple representing a finite automata where Q is a finite set of states, Q0 is starting state which belongs to the Q, A is the set of accepting states, okay, sigma is the input alphabet, and delta is the transition function. All right, so those who have not taken a automata theory course or computational complexity theory course, it might look like an alien for you guys, but nevertheless it's a very simple thing that it's a state machine, okay. Finite automata or automation, it's a state machine, okay, and the state machine has a characteristic, okay, and those characteristics are the properties of a state machine. We can represent by this five tuple, okay, that it has the machine, state machine will go to different states, okay, and those are finite states, okay, and then it will start in some state Q0 and it will stop, or it will say it will accept your input pattern or a string and will go to some accepting states which are represented by A, which is a subset of Q, and sigma is the input alphabet. Um, we discussed about input alphabet in the previous lecture, and it's simple that what basically your string constitutes. Say it may be simply 0 and 1 if your binary string, and that becomes the alphabet for your binary string. If you have a decimal string, then it will go 0, 1, 2, 3 up to 9. Okay, so that's your alphabet. Or if you have, say, text string, you can define, okay, my text string will have only these many characters. Okay, like in this example, I have defined the input alphabet has only E and F characters. So all these strings would be made of E and F, okay, in different order. And then delta is the transition function, which says that, okay, if I am in certain state, okay, and if I get an input E, in which state I will have a transition. That's simply a transition function, say, or mapping function, okay, that in a certain state Q, and upon inputting certain alphabet character, I move to a different state, okay. Now let's look at the example. So it's a very simple finite automata, a state machine which accepts a pattern EFE, all right, and 0 is the starting state and 3 is the final state or accepting state for this small automata, right? So initially we are in state 0 and the input pattern E occurs, we move on to the state 1. Okay, we are in one state as long as we have E, and if F comes, we move on to the second state, and then if E comes, we move on to the final state. Okay, now if we are in second state and if F comes or any other input comes which is not desired to go to third state, we go to by default 0 state. Okay. And if we are in final third state and E comes, we go back to the 1, and if F comes, we go back to the 2. And this small state machine accepts this pattern EFE. All right. Now let's see what is the transition function. Okay, so this table shows us the transition function delta for this small state machine. As you can see here, this is the state 0, 1, 2, 3. Okay, leftmost or say these are states S, and these are E and F is the alphabet characters. So if we are in state 0 and input E comes, okay, we are in state 0, input E comes, we move on to the state 1. F comes, okay, which is not desired in our pattern, then we go back to the default 0 state. Second, if we are in state 1 and input E comes, we stay in that same state, and we are in state 1, F comes, we move on to the second state, and so on. In the same way, if we are in state 2, input E comes, we go to the state 3, and F comes, we go back to the default state. That's not desired input for this pattern string. In the same way, if we are in state 3, which is also our accepting state, if E comes, we go back to state 1, F comes, we go back to state 2. And this small state machine will accept the pattern P, which is E, F, E. All right. We can also say that the delta, okay, transition function, Q is the state, X is any input alphabet character, is the same as a function of PQ or X. PQ here just simply stands for the what pattern we have read, okay, when we are in state Q. So if we are here, say if P1, okay, so in P1 state, we have read only E value, okay, so P1 would be E. Okay. What is P2? So P2 simply says that we are in state 2 and how many minimum characters we have read to reach to state P2 is simply we have read E and F. So EF would become P2. It's a very rough sense. So to get a formal definition, you can check your textbook. But I'm just discussing here in a very simple and general rough sense what is P1, P2, and so on. Okay, and X is simply the input. Okay, so if we are, for example, let's say delta transition function 2 and E. Okay, 2 is the state and E is the input character. Okay, equal to 3. What it means that P2 is E and F. We have read the characters E and F. Okay, that's P2, and input character is XE. So that would become EFE. Okay, P2E EFE, and sigma P2E is equal to 3. We move on to the state 3. These are certain notations which are given in textbook, and just a simple explanation for these notations. All right. Nevertheless, it's a very fantastic class of algorithms and very simple algorithms. Now, see, the beauty of finite automation based algorithm is that Once you have constructed this this state machine, or this transition function or transition table for the state machine, which recognizes this pattern, then your job is very simple. Your algorithm will take a linear order for this text string. You just have to read only once the characters of the text string, and you will come to know that whether this pattern occurs in this text string and at which places it occurs. You just have to process the text string only once. So whatever time is spent in constructing the transition function, okay, or this finite automata. And for searching and matching pattern, it's a linear order. So it's a beautiful class of algorithms, right? Now let's talk about algorithm. So first step for uh, any finite automation based algorithms is the pre-processing step. And what is pre-processing step? As we discussed just now, that we construct a string matching automata for the given pattern, or in other words, we create a transition table, okay, for for a given pattern. That's the big thing for this class of algorithms. Otherwise, the algorithm is very simple. As you can see in this algorithm, finite automata based string matcher, it will take T, your input text string, transition table, and P, your pattern. Okay, and simply you just go from for whole length of your text string, okay, and see if and match that text string each character, okay, and check what is the transition function, okay, from the transition table. And in the end, if you say, okay, I have fully processed my text string, and I see the value of the output of the transition function, which is a state, is equal to the length of your pattern m, then you have discovered the pattern with a shift I minus m in the original string. All right. Essentially, the complexity goes back to the how to find the or how to construct the transition function table for the given pattern, okay, and which is not very difficult. It's just we need to pay a little attention that okay, how do we do that? So those algorithms to find the transition functions, these are based on suffix or prefix. So in this basic transition function algorithm, we're going to be focusing on finding the longest length suffix, okay. What it means that that we try to find the maximum length string, which becomes the suffix of the string, which is in certain state the string pq, which is the string of the characters in a certain state q, and x is certain input character, okay. So how the algorithm process is very simple, that for the whole length of your pattern, okay, you go from for the whole length, and then for each character, okay, in each character in your input alphabet. So m may be 4, 5, 6, and your alphabet may be 2, right? And then you define a variable k, which is minimum of m plus 1 and q plus 2, and you repeat this step 6 until you find a suffix, okay, suffix pk which is suffix of the string which is represented by PQ and X. We discussed what does it mean by the PQ, P1, P2, P3 in the previous page. Okay, and then if we repeat that step, and in the end, whatever value is left for the K, that becomes the transition function value, okay, for that input character in that particular state Q. And we just return the transition function. Okay. So if you notice here that we are running one for loop, second for loop, and this repeat loop. So essentially we have here three loops. Okay, and these three loops have say first is very simple, it's running for m times. Okay, then second is how many characters you have in your alphabet. Okay, and third loop, on an average it will come down to the length of m. So if you see the complexity of this transition function, it's basically is nothing but m cube. Okay, 3 times you are running the for loops multiplied by how many characters. Okay, for each character you are running here, how many characters you have in your input alphabet. So the complexity of this algorithm to find the transition function or transition table for each state and input combination is in the order of m cubed and delta, while the string matcher is a linear order. Okay? You just have one for loop and you just process the whole text string once and find out what is its transition function for each character in the input string. And if you find the value which is equal to the length of the string or length of the pattern m, then just say I found the pattern. So very simple. Now let's try to find out how this transition function algorithm is going to work on our very simple example string. Right? As you can see, we discussed this very simple example EFE, the very first page or very first slide of this lecture. So let's try to map just few steps, and then rest of these steps you can figure it out. So the algorithm starts with the q is equal to 0. Okay, so when q equal to 0, first character, or let's say if input alphabet or character x is e, then your k would be minimum of m plus 1, where m is your m is 3. Okay, m is 3. So 3 plus 1 is 4, and then q is 0. 0 plus 2 is 2. Okay, so we get k 2, and then we repeat this step. Okay, because we repeat this step until k equal to k minus 1, 2 minus 1, 1, until we find that pk, so p of k is 1, okay, is equal to e. So p of 1 simply says that at this state p, how many character strings we have read is e, and then p q x. So q here is 0, so p 0 e is equal to e, because there is at the state 0 we have no character left, so only e. Okay, and which is a suffix, we find the suffix, so we can say that simply delta 0 e equal to 1. Okay, now let's take next character in the input alphabet set, which is f. So x is f. Okay, we are again go back to the loop 3 here. So k is 2, and then we decrease the value of the k, okay, and then we find the p1 equal to e p0f. Okay. So p0f is equal to f, okay, because p0 there is nothing here, and f is f. Now e and f, so e is not the suffix of f, okay, e is not the suffix of f. Then we simply go back and repeat k equal to k minus 1. So k equal to 1 minus 1 equal to 0, okay. Now we see that the p0, okay, here p0 is nothing and p0f is f, okay. So 0 or null string basically is a suffix of any string, okay, and delta 0f equal to 0. So we find the delta 0f equal to k equal to 0. Now let's say the next q value. So when q equal to 1, okay, and input is e, now here simply what would be the value of the k would be minimum m plus 1 and q plus 2. So m plus 1 is 3 plus 1 4, and q plus 2, q becomes here 1 plus 2 is 3. So k becomes 3, and then we are in the repeat loop, k equal to 3 minus 1 2, and let's try to find out what is p2, okay. So p2 that we discussed earlier, what is p2 is the string or the characters, what characters we have read till we reach to the state p2 minimum characters e and f. So p2 is ef, and then pqx, q is here 1, okay. So p1e, p1 is e, and then e, okay. Now here you see p2ef is not suffix of ee, so we go back and decrease the value of the k equal to 2 minus 1 1, and then we try to find out value of the p1 is e. So now here p1 is e and p1 e is ee, okay. So we have here ee and e. So e is suffix of ee, okay, and we stop this and we find out that, okay, delta q is 1 and e is equal to 1. All right, now let's say q is 1, and for each character, third step loop, so next character of the input alphabet is f, k is 3, k, decrease the value of the k becomes 2, p2 becomes ef, and p1f is equal to ef, because p1 is e and the next character is f, so p1f is ef. And you see here the p1f ef is, and p2 is ef, so p2 becomes the suffix of p1f. All right, so p2, this is string ef, becomes a suffix of p1f, which is ef. So simply it means that we find our transition function delta for 1 f is equal to 2, okay. And same way we can, similar execution steps for other states, q2 and 3, okay. We discussed 0 1 and 2 and 3. You can do it by yourself. It's not very complicated. All right guys, so thank you very much. Hope you guys have learned and enjoyed this lecture. Thank you once again for subscribing and liking lectures on LeProFesseur YouTube channel. Those who have not subscribed, please do subscribe. We appreciate your feedback and support. Have a wonderful day.